Hello, today I'll be reviewing the status of experiments into quantum supremacy, and this relates to both the algorithmic aspect of what problems quantum computers are able to solve efficiently, but also the theoretical aspect of delineating a difference between classical and quantum computational complexity classes. So the first problem that might pop into your head when you think about quantum supremacy is, isn't it obvious that quantum supremacy has already been demonstrated? For example, Shor's algorithm shows an exponential speed up in factoring primes, specifically by implementing the quantum Fourier transform. The thing about Shor's algorithm, though, is that it's much too complicated to experimentally demonstrate, to implement, because it requires too many qubits. And other algorithms as well, for example, Simon's algorithm, require oracles, and we need to implement these oracles in a way that preserves an exponential speedup over classical computing, and this has not been shown to be possible with Simon's algorithm. So ultimately, the problem that we want to find a problem that will give quantum computing an asymptotic speedup over classical computing, ideally with near-term noisy quantum computers. And if such a problem was found and proved that classical spoofing claims, which are basically claims that classical computers can do the same thing, are not possible, that they are not valid, then that would be an example of a demonstration of quantum supremacy. And such a demonstration would violate the extended Church-Turing thesis, which states that any algorithmic process, classical or quantum, can be efficiently simulated by a probabilistic Turing machine, where efficiently means in polynomial time. But note that it would not violate the original Church-Turing thesis, which doesn't deal with complexity but merely with computability. So I'll be reviewing two approaches that have been taken to showing quantum supremacy. The first is random circuit sampling, and the second is boson sampling. So for random circuit sampling, you take n qubits, say all in the computational zero state, and then pass them through a random circuit, which is just a series of gates with no particular purpose, just randomly generated, and then take a measurement of the final bit string, n bit string, and for any given random circuit, there will be a distribution of k bit strings that you expect based on your measurement. So we're going to sample that distribution by taking a sample of size k of those bit strings, and then we use a classical computer to compute this cross entropy benchmark, which is defined as 2 to the n times the expectation value of the probability of measuring any given state xi, all minus 1, and the expectation value is taken over all k. So on the right-hand side, this is expanded out. The term in parentheses is essentially summing instances of Born's rule, where C here is an ideal, noiseless, errorless quantum circuit, taking the state of n zeros to any given state x sub I, and we sum that over all states with summation index I and divide by the number of states k to give a kind of mean, and minus 1 so that the ultimate xeb is between 0 and 1, where 0 represents random guessing, which is just useless, and 1 represents a perfect quantum computer. So the primary group that is pursuing random circuit sampling is Google. They've demonstrated a computation with a 53 qubit processor, which they call Sycamore, and they've done this computation in 200 seconds, claiming that it would take 10,000 years classically, with an XEB of, it seems rather low, but actually it's still an order of magnitude higher than other demonstrations of 0.0024, but the fact that it's so close to 0 really shows that there is a lot of noise in the current experiments that try to demonstrate quantum supremacy. The thing is, though, that IBM has used their supercomputer, their classical supercomputer, which has a lot of disk storage memory, like petabytes of disk storage memory, to claim that it would be possible to do this computation classically in only 2.5 days, which is still a lot more than 200 seconds. But since they managed to turn 10,000 days to 2.5 days, you can only ask whether or not it's possible that further speedups would lead to a scale of hours or minutes, in which case quantum supremacy would not be obviously demonstrated. But in general, quantum classical simulation claim, a spoofing claim, for a random circuit scales exponentially with the number of qubits, and so if there was an efficient classical simulation, that would collapse the polynomial hierarchy. So we believe quite strongly that there is no classical simulation in general efficiently in polynomial time. The alternative method for demonstrating quantum supremacy is boson sampling. And for our purposes, bosons are just integer spin particles. They're unrestricted by the Pauli exclusion principle. So classic case photons, meaning that multiple photons can take the same quantum state at the same time for any given system, which is different from fermions, which for a given system, no two particles can occupy the same state. And this means that when we send photons into a system, they're indistinguishable, and if we send them in simultaneously, they're truly identical, and they pass through, in this experiment, they pass through a linear interference grid, which is composed of beam splitters and phase shifters. So beam splitters take a single photon and put it into a superposition. They split it into a superposition of two states. You can essentially think of this as just a Hadamard, and phase shifters as phase gates. So the experiment is to send in these indistinguishable simultaneous photons and then sample the output distribution. There's a classical toy analogy of this, which is shown as the left panel of the figure at the top. It's called a Galton board. You might not have heard of that name, but you've probably seen this, where if you put a lot of tiny metal bearings into a grid of diagonal pegs, the bearings have a 50-50 chance at every single peg of going left or right, and so they form a binomial distribution with success rate 0.5. And obviously the quantum distribution is not as simple as a binomial distribution, and one example of the way in which quantum effects take place is something called the Hong-O-Mandel dip, which is namely where if you have two photons simultaneously reaching a beam splitter, they will both be directed the same direction. They will take the same state. They will not go separate directions, and so that's a fundamental property of bosons, which tend to congregate together into the same quantum state. And the classical algorithm, the best classical algorithm that's known for boson sampling, predicting a sampling distribution of boson sampling, is for n photons and m output modes, where output modes are just the boxes that you eventually measure the photons in, is of order n times 2 to the n plus mn squared. So essentially exponential in 2 to the n, and usually m is significantly larger than n of at least order n squared. And the implications of boson sampling are that although it is non-universal, it is a stepping stone towards a universal computation scheme. So specifically KLM, the KLM scheme demonstrates that if you add adaptive measurements to boson sampling, so if you allow measurements at intermediate stages of a circuit which might affect later stages through, for example, taking a C0, that gives you universal computation. But the thing that's difficult about boson sampling classically is that it requires calculating permanence of matrices, and the permanent is a property similar to the determinant, except that all of those minus signs which you usually take when computing different permutations of the cofactors, there are no minus signs, there are only plus signs. So for example, the B cofactor here is BFG plus BDI, there is no minus sign there, and also the cross product itself, taking for example AEI plus AFH rather than AEI minus AFH. So the permanent is actually harder to calculate than the determinant, because in the determinant many terms will cancel out with the minus sign, making it relatively simple to approximate, whereas the permanent sampling, the boson sampling, in order to calculate these permanents, even if you include the effects of noise, which would make quantum computers less perfect, it's still expected to be a problem that's in the computational complexity class sharp P, which is at least as hard as NP. So sharp P asks the question of how many solutions there are to a problem. So for example, how many disjunctive normal form sentences there are that satisfy a given, or for example, how many SAT sentences satisfy a given problem, a given SAT problem. And so that's obviously harder than simply asking whether something has a solution or whether a solution can be verified. And so if there was a classical simulation of boson sampling, that would imply collapse of the polynomial hierarchy to its third level, where the zeroth level is P equals NP. So that shows that we really don't expect there to be a classical algorithm for boson sampling. So now to compare boson sampling and random circuits, the main benchmark that's used was the linear XCB that I introduced earlier, but actually there are other benchmarks, which just go to show how subjective it is to be determining whether a demonstration of quantum supremacy has actually been achieved. One of these is the heavy output generation test, which is just the proportion of unique samples with a classically computed probability higher than the median or mean of the probability of the distribution. So we use a classical computer to try and model the distribution and take the mean of that. And if a quantum computer is generally outputting the more likely output results, then that shows us that it actually is doing a proper modeling of the underlying distribution, rather than just like randomly throwing out states, which would likely lead to a relatively low proportion of such samples. Another benchmark is total variation distance, which is just a standard measure of the variation between different probabilistic distributions in statistics. So in the figure on the right, it's proportional to the shaded area between the two distributions. And this total variation distance benchmark was originally supported by Scott Aronson as the benchmark to use on boson sampling experiments. However, he later realized that boson sampling using this benchmark doesn't work very well, because boson sampling experiments, their main advantage in quantum computers is that they can effectively calculate high order correlations, where high order means that there are correlations between a high number of the output modes, the output bins, and obviously, like classically, if you run beads down a Galton board, it's pretty easy to know that generally there will be a bell shape, but specifically finding out which exactly like how the number of photons output in one bin depends on the others is something that's much harder classically. And the thing is, current quantum experiments don't show that correlation very well on low order correlations, which means that a classical spoofing attempt could easily just do well on those low order claims, which are easier to simulate, and completely ignore and don't even try to approach the high order correlations, which means that total variation distance isn't such a good metric for actually demonstrating that. And for example, USTC, which is a China-based group which has tried to use boson sampling, is arguing that you should subtract out the low order correlations and only focus on the high order ones to define a new kind of benchmark, which obviously Google is not very happy about. They consider that moving the goalposts after the fact. But that just goes to show that these benchmarks like linear cross entropy can be easy to spoof classically by only accurately simulating the parts that we know to be easy to simulate and ignoring other conditions which are unique to the quantum system. So in conclusion, there have been two main attempts at quantum supremacy. There are others, but the two main ones are random circuits and boson sampling. Random circuits are easier to benchmark, they're easier to define, because in random circuits, only the highest order correlations are non-trivial. We really don't care about the other ones, because if you trace out any given qubit, the reduced state you're left with is exponentially close to a maximally mixed state, so it doesn't really give you any additional information. Whereas in boson sampling, it's hard to determine whether we should be using benchmarks based on the lower order or higher order correlations. But in general, for both of these methods, there are various directions that can be improved in current and future work. So first, statistically, how to verify that a sample is in fact a successful quantum simulation, because, for example, Google claiming that it would take 10,000 years, we need to be able to verify that result in less than 10,000 years. And so IBM claiming that it can do it in 2.5 days is actually excellent support for demonstrating quantum supremacy, because it shows that if it was actually carried out and showed that the quantum supremacy experiment was correctly carried out, then we would have higher confidence in the results, because even Google could not have biased their results to play to the test, because they were not able to run that test themselves. A second direction for future research is asking theoretically how much noise reduction is needed for boson sampling to evade spoofing, and corresponding to that experimentally how the higher order correlations can be amplified, so that we can actually see the areas in which quantum computing might have an advantage. But both of these are relatively toy systems that are attempts at demonstrating quantum supremacy, but they're both useful at hopefully eventually demonstrating how universal quantum computation can be feasible, and as I said, as a stepping stone towards that universal quantum computation. So thank you for listening.